Okay, let's go ahead and get started. I want to address one confusion that came up when people came and asked me questions after class about the whole definition of what makes a language regular. So, if you remember from lecture, and zoom out, and focus. Okay, good. Okay, so a language is regular if it satisfies one of these 5 conditions. Either it's empty, it has exactly one element, it's one string. It's the union of 2 regular languages, it's the concatenation of 2 regular languages, or it's the Kleene star of a regular language. And one of the bits of confusion is if you look at the definition of the Kleene star, well, it's the set containing the empty string, union A, union A dot A, union A dot A dot A, union, and so on. Okay, so it looks like the Kleene star is the union of regular languages, because each of these terms in the union is the concatenation of several copies of the same regular language, so by rule 4, each of these components is regular. And then I'm unioning them all together, and we know that the union of regular languages is regular, and this component here at the beginning is regular because it has size 1. So why did we need the 5th rule at all? Why do I bother to write line 5? Why doesn't that follow immediately from the first 4 lines? Anyone? How many people were confused by this point? At least 3 of you should be raising your hands. Don't feel like you have to, because I've already seen you. But anyone else confused by this point? Okay. Mm-hmm.
A, does that mean take any string in A?
That means take any string in A and concatenate it to any string in A. So the 2 strings are not necessarily the same. Think of the A's as like 2 different copies. Right. So why do I need to specify the rule 5 that if L is this infinite union of regular languages, that the result is regular, as opposed to just saying, well, that follows from the other 4 rules, or 3 of the other 4 rules? And the answer is something very subtle but very important about recursive definitions, which is that whenever you look at something that have a recursive definition of something, eventually, as you bubble down the recursive cases, at every branch of recursion, you must eventually reach a base case in a finite number of steps. Okay? So you can build up, from rule 3 here, you can build up unions of 3 regular languages, and 4 regular languages, and 17 regular languages, and 374 regular languages. But you can build up unions of n regular languages for any integer n. Infinity is not a number. In particular, it's not an integer. There is no way to recursively construct, if you will, a union of an infinite number of sets by composing unions of, a finite number of sets. And there's a similar subtlety just in the definition of a string. Right? What it means for W to be a string over the alphabet sigma is either W is the empty string, or W is this ordered pair AX for some character A in my alphabet and some string X over sigma. So this recursive rule allows me to construct strings that are arbitrarily long. I can choose to invoke rule 2 as many times as I want, as long as the number of times that I want is actually a number. Right? I can decide I'm going to invoke rule 2 17 billion times in a row, and then I'm going to get a string of length 17 billion. But I can't choose to invoke it an infinite number of times because infinity is not a number. Strings are always finite. They're unbounded. There's no limit on how long they can be, but all strings are finite. Similarly, if I only allowed these first 4 rules, then every regular language would be finite. It would have a finite number of elements. I'd either, I'd start with sets of size 0 and 1, and by taking unions, I could add their sizes, and by taking concatenations, I could multiply by their sizes. So I would always get sets that had some integer number of elements. The only way that I can get infinite languages is by having an operation like this star that explicitly produces infinite sets. Right? So this is something that, at some point, there's this transition between, oh yeah, sure, I understand when I invoke this recursive algorithm for, say, sorting an array, that eventually it has to bottom out. I'm sort of comfortable with the idea that in a recursive algorithm, eventually, no matter where you recurse, it has to bottom out, or you get stuck in an infinite loop. And then it's not a real algorithm. When you start applying it to definitions, somewhere that connection gets lost. Okay? So this is really important. There's no bound on how long a string can be, but every string is finite. There's no bound on the size of the set I can get by doing pairwise unions, but I can't get an infinite set. All right. Any questions about this? Hopefully, some of you were helped by this, but if you're now more confused than ever, please, feel free to come up after class and ask me what the hell I was talking about. Okay, so the other thing that I want to say about the lecture on Tuesday, in retrospect, context-free grammars really deserved their own complete lecture. That went by pretty fast, and if I haven't lost my ability to smell the sense of the room, it went by fast enough that it didn't really go in. We're going to do some practicing with building some simple context-free grammars in a section tomorrow. But basically, I'm going to have to rely on you. If there's a point that you're confused on, especially with the homework, please ask. Please ask on Piazza. Please ask in office hours. Please ask early. We're going to let I'm going to let the homework ride to see how it goes. But as with everything in this class, if it turns out that the most common answer that I get is I don't know, that's a good indication that it's not really a fair question, given what I've already told you. We are going to be looking at context-free grammars again as examples later in the course. Hopefully, again, as those come up, please let me know if there are any questions. Okay. But the nature of this course is that it is far too packed, and we've had to throw out far too many things already. And so without some considerably more significant planning, I don't really think it makes sense for me to try to spend another half an hour covering context-free grammar is way too fast. So I'm going to move on to the next thing. Okay. So to start out, here's an algorithm. I want to just start by giving you an example of the kind of thing I'm talking about. Okay. So this algorithm, multiple of 5, takes as input an array which I assume contains bits, 0s and 1s. Okay, so this is a string, if you will, over the alphabet 0, 1. And the goal of the algorithm is to determine whether this string of bits represents a number that is divisible by 5. Okay? Now, the way that I'm going to do this, I mean, one way that you could imagine doing this is you could say, well, I have a division algorithm. I have a standard algorithm for doing long division that everybody pretends to learn in the 3rd grade, and I could turn that into an algorithm that has a for loop and does bell borrows and carries and so on. But I'm going to do something slightly different, which requires me to use less memory. I don't want to keep an array for the result and then figure out what the remainder is. I'm only going to keep track of the remainder. Okay, so I have this variable rem that is the remainder, and what it really represents is the remainder of the part of the string I've read so far when I divide it by 5. Okay? So the idea is that if I have some number n, and then I read a symbol 0, that's the same as 2 times n. And if I have some number n, or maybe I should call this m followed by a 1, the value of this is 2m plus 1. So what I'm doing here is essentially saying, if I think I know what the remainder is for m mod 5, and I read one more bit, this line tells me the remainder of either m0 or m1, depending on which bit I'm reading. Okay? If I wanted to do multiple of 7, the only thing I would have to change here is the 5 to a 7. The 2 here is because it's in binary. Okay? Does everybody understand, vaguely at least, what the algorithm is doing? Okay, the important feature that I want to mention about this, point out about this algorithm, is that aside from the variable I, which is just a counter that scans through the input string, there's only one variable in this algorithm. And it can only have a small number of possible values. Okay. So algorithms like this that have this character where you're running through some long stream of characters or symbols or TCP packets, and you have a small amount of memory, are sometimes referred to as streaming algorithms. I want to monitor the internet backbone, and I want to count how many times somebody looks up google.com. Okay, so maybe I have a counter, and that's it. Okay, but I'm really thinking about an extreme version of streaming algorithms here. The data is going to fly by. You're allowed to remember a few things, but essentially the intuition you should have is you're allowed to remember things on your fingers. You're not allowed to write down numbers. You're not allowed to count to 1,000 because you only have 10 fingers. So you're allowed to have variables, but any variable you have has to exist in a finite number of states. And I should be able to write down how many states that variable has at compile time. Okay? So I can compute, for example, whether a given binary number is a multiple of 5. I can compute whether a string of 0s and 1s has an even number of 0s. Every time I have a 0, I flip a bit, and that bit is my internal state. I could decide with a little bit more effort whether a string contains a particular substring by just looking at the last few characters as I go by. Yeah?
Could you please explain how this relates to streaming algorithms again?
Okay, so the idea is, what the for loop is doing is essentially allowing the algorithm to look at the data one piece at a time. And when A sub 5 goes by, W sub 5 goes by, it's gone forever. I'm not allowed to remember it. So you can imagine generalizing this to, I have a terabyte an hour of internet packets going by. I can't store more than, say, 10 of them, right? And still I need to be able to compute something interesting about that packet stream. Okay? So, a more interesting way that I might describe this is, well, I'm going to have an algorithm that does something. I don't know what it is yet. And I'm going to start out with a variable called Q that just encapsulates the state of my algorithm. Maybe Q is a number between 1 and 4. Maybe Q is a set of ordered pairs where the first element in the pair is a letter of the English alphabet, and the second is a vector of 5 bits. Something where I can say, this variable has at most 38,000 values. Unbounded, but not infinite. Okay. And then I'm going to just scan through the input, and based on the character that I read in the input at position I, I'm going to change my state. So I'm going to have this function which, to give you a mnemonic as change, for whatever reason, historically this function is called delta. And this function takes in, the current state and the next symbol. All right, and then finally, I'm going to imagine that I have some output array hard-coded into the algorithm, and based on what the state is when I've finished reading the string, I'm going to output whatever's in the array at that position. Okay? Now, the important thing here, this is not a function that I'm calling really. This is, you should just think of this as a lookup table. Okay, so for example, the lookup table for multiple of 5 is if I'm in state 0 or 1, or sorry, if I read 0 or 1, and I'm in state 0, 1, 2, 3, or 4, so this is Q, and this is the symbol A that I'm reading, so I should go to 2Q plus A, 0, 2, 4, 6, but mod 5 is 1, 3, 1, 3, 0, 2, 4. Okay, so this is my transition function for this particular algorithm. In this case, I've called the state variable rem instead of q, and instead of using this funny delta notation, I actually explicitly wrote the function out. But and I think somewhat more generally, instead of doing arithmetic at all, I could just hard code this 2x5 array into the code and then do a lookup. And in fact, arguably that would be faster. Right? And then in the end, notice I'm just returning true or false depending on whether the remainder is 0. So for that particular algorithm now, A of 0, 1, 2, 3, 4 is true, false, 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 false. Again, this is just hard-coded into the algorithm in the source code. Okay. Now, this sort of general algorithm for let's scan through an array, and every time we read a symbol, do some computation, but do it in a way that our internal state, represented by this letter Q, always fits within some small set of values. This is called a finite state machine. Now, in this kind of formulation, it maybe makes more sense to call it a finite state algorithm. But keep in mind that an algorithm is a machine. It is a description of a machine. That has, the variables represent various, you can think of it as representing various physical quantities in the machine. In the case of a finite state machine, it's like, there's a dial in various positions. I could actually imagine building a physical thing out of gears and wires and springs and rope and mice that I push the button 0, 1, 0, 1 at the top. And whenever I've typed in a multiple of 5, the light bulb on the front of the box goes on, and whenever I haven't, it goes off. Okay? So for this reason, it's called a finite state machine, right? And this formalism was developed, back in the 1940s and 50s, when machines really meant things the size of this room. They weren't little things you could just put in your pocket or wear on your face, right? And the other word that's attached to this is comes from the idea that it's a machine that you don't have to monitor, you don't have to adjust, you don't have to, once you've programmed the rules in, everything proceeds automatically. Automatically. Right, so an automaton is a device that acts on its own, from the Greek roots. So automatic, it means something that happens by, on its own, as if by an automaton. Okay? So, I want to show you another way of picturing exactly the same machine. Brakes. Yes, clearly this projector is also a finite state machine. Okay, so that is that little picture of circles and arrows with numbers on them. This is also a description of exactly the same finite state machine. Now, what the semantics here are is the program, each of those circles, each of those nodes in the graph I've drawn here, represents a possible state for the algorithm, possible value for the variable rem. Give me 0, 1, 2, 3, or 4. If I am currently in state 0, and the next symbol that I read from the input is a 0, then I stay in state 0. 2 times 0 plus 0 is 0. But if I read a 1, I should transition to state 1. Similarly, if my current state is 3, the number I've read so far is congruent to 3 mod 5, and I read a 1, then if I just grind through the math a little bit, you'll realize that I should transition to state 2. Okay, if I take a binary number that's congruent to 3 mod 5, and I add a 1 to it, I get a binary number that's congruent to 2 mod 5. And so now I can, just throw the math away and say, I've got a graph, right? This is like a small and somewhat more complicated version of Candyland. I start with my token on square 0. I draw a card. If it has a 0 on it, I follow the 0 arrow back to state 0. If I draw a card and it has a 1 on it, then I follow the 1 arrow out to state 1. And I keep drawing cards that have 0s and 1s on them, and every time I draw a new card, I follow the arrow leaving my current state that has the value on the card. Eventually, I run out of cards. The input is done. At that point, notice that state 0 has this doubled circle around it. That is an indicator that I should say, yes, I accept. This is a multiple of 5, versus the ones that have single lines around the circles. Those are not acceptable states to be in when you're done. And so if I run out of cards and I'm in one of the states 1, 2, 3, or 4, then I say, no, that wasn't a multiple of 5. Okay, so when I run out of cards, if I'm on a double circle, I win Candyland. If I end up on a single circle, I lose Candyland. Okay, except it's not just Candyland, it's any graph. So I can specify a finite state machine by just putting down a graph, and the only constraint that I need is that for every symbol that I could possibly read in my input string, and for every state, every node in the graph, I've got an arrow leaving that node that has that symbol on it that tells me what symbol to go to next. Now, these two representations of the algorithm, of the machine, you've got one here that is just, well, it's a lookup table that the algorithm could use, or that the machine could use, that specifies the behavior of the algorithm formally. And you've got this graphical representation that specifies it also formally. I mean, you can define the graph formally as, here are the vertices, here are the edges, here are the labels on the edges. This vertex is the one that you start at. It's got an arrow going in. These are the vertices where I say yes, because they've got double circles. Depending on what you're trying to do, one or the other of these representations is going to be more useful, right? For the sake of intuition, it's generally easier to think about building things as graphs and drawing pictures and pointing at the whiteboard and saying, this state means, and then writing something in English above it. But when you're trying to prove things about finite state machines in general, it turns out to be easier to use this sort of more functional looking notation with the confusing Greek letters, simply because it allows you to be more precise about what you're talking about. Okay? So let me give you the sort of formal definition with the confusing Greek letters. It's not really that confusing as long as you accept the letter delta into your heart as an actual letter, and not, something that Satan is trying to confuse you with. Okay, so a finite state machine is a collection of 5 things. Okay? Something familiar. It's an alphabet, sigma. This is specifying what the input's going to look like. The input's always going to be a string over this finite set. And again, this can be any finite set you want. This can be the letters of the Latin alphabet, it could be the people in this room, it could be the hairs on my head, anything. Okay? Okay, I have another set Q of things that we call states. Right, so in our multiple of 5 algorithm, the states are the integers 0, 1, 2, 3, and 4. For other algorithms, these states are going to be more complicated. Generally, when you're thinking about this, you're not going to decide, I'm going to try to build here, I'm going to decide on the alphabet that's going to be given, I'm going to decide on the states, now let me try to figure everything else out. The states are something that you need to figure out when you're trying to design the finite state machine. They eventually will sort of fall out of the design. There's S, which is a start state. Sometimes, for historical reasons, this start state is called Q naught. Right, so this is, an element of Q. Okay? This is where you, the initial value of your internal variables, the node that you start on. So you have a set of accepting states. Again, this is a subset of Q. For historical reasons, this is sometimes called, actually no, it's for historical reasons it's not called F. For some reason, these states are called final. And even in the initial paper that described these finite state machines, the authors said there's a set A called final states. And it's especially weird because neither of the authors speak a language in which the word final starts with an A. So we're just going to call them, A for accepting. If you want to call them final states, great, but then call the set F. Okay. And then the most confusing part. Okay. Transition function, which is always called delta as a mnemonic for change. The arguments for the transition function are a state and an input symbol, and the output is another state. So these are the things that are represented by the arrows in the graph that I showed you earlier. Yes?
What does the little X represent?
It's the Cartesian product of those two sets. Okay, so an element of the set Q cross sigma is an ordered pair whose first element is a state and whose second element is a symbol. Right? So if you look here, I've written it here with brackets instead of parentheses, but that's what it looks like. Yeah?
I have a question. Doesn't necessarily mean that there are states from every single state to another, or to different transitions. For example, if you looked at state 4, you couldn't go to state 1.
That's correct. What it means is no matter what state I'm in, and no matter what character I read next, there is a state that I go to. Right? Given a state and a symbol, there is a corresponding next state. So for every node and every symbol, there's an arrow leaving that node labeled with that symbol. But there's not necessarily an arrow directly from 4 to 0. Okay? So again, if...
When you say the Cartesian product, doesn't it mean all the states?
Yes, it means all the states, including the one where it gets stuck zooming in. The Cartesian product is Q cross sigma, states cross symbols. For every state and every symbol, there is a next state. Right? For the state 3 and the symbol 1, the transition function returns 2. For the state 4 and the symbol 0, the transition function returns 3. What I'm not doing is saying, for the state 3 and the state 2, the symbol I want is, that's a different function.
Okay.
Right? Okay? All right. And yes, automatically focus without any manual intervention. Okay. So this is what a state machine is. This is the syntax. When you want to specify what a state machine is, you need to specify all 5 of these things. Now normally when I say, design a finite state machine that accepts strings of 0s and 1s with the blah, 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 some property, you know immediately what sigma is. It's the set 0, 1. And so arguably you don't really need to write that one down. But everything else you have to write down in some form. One way that you can write it down is by writing down a graph where the symbols are the states are the nodes, the transition function is encoded by the arrows, the start state is the one that has a free arrow pointing to it, and the accepting states are the ones with double circles. Another way you can specify it is by explicitly writing down the array that specifies the transition function and a list of the states that are accepting. Yes?
When you look at the table, how do you specify start
you have to write that explicitly. Right. So in this case, I would, all I really have to do is write that. All right. And then implicitly, the states are the things on the left. Now, more often, you know, if I said, okay, show me the set of, I want a finite state machine that accepts all numbers written in base 10 that are divisible by 127. What I do not want you to do is to show me a 10 by 127 table. Right? In that case, what I want you to write is something that looks more like this. Right? The transition function is a function. In this case, it's a, you know, it's a nice, simple mathematical function. This way. Okay, there it is. Right? So that black box, together with the statement that, well, the states are 1, 2, 3, and 0, 1, 2, 3, and 4, and the start state is 0, the accepting state is 0, that describes the finite state machine completely. Okay? Now, okay, this is all syntax. This is all how you specify the machine itself. But I also need to tell you the semantics, how the machine actually works. What does it mean? How do you interpret these functions? Okay, and so to do that, let me define a somewhat more complicated function. All right, so this is sometimes called the extended transition function. And as usual, I'll specify the function in English first. So QW, this is the state reached by my finite state machine if we start in state Q and read process string W. Okay? So delta of Q comma A is the state reached by the finite state machine if I start in state Q and I read symbol A. That's specified as that's what this transition function actually is. It's part of the definition. So I can derive from that definition this more complicated function. Now I can actually give you the recursive definition. And the recursive definition is, of course, going to rely on the recursive definition of one of its arguments. Which argument? What are the cases going to be in this definition? Yeah.
String.
Yep.
Like epsilon and
Okay, so there are two possibilities for the string W. Either it's empty or it isn't. Okay, what do you think we should do if I start in state Q and I read nothing? Good, you all got it. Nothing. If I start in state Q and I don't read anything, I don't do anything, then I'm still in state Q. Yes?
What about for silent transitions?
For now, we're not going to admit silent transitions at all. When we start talking about non-deterministic machines, then we'll have silent transitions, or as they're usually called Epsilon transitions. But here, the only, for this model of finite state machines, the only time we can do a transition is when we read a symbol. And when we read a symbol, we must do a transition. Okay? So the other thing that we can do is we can get a non-empty string. And in that case, the first thing that the machine does is it transitions from Q to whatever the transition function tells me is where you should go when you're in state Q and you read the symbol A. And then the next thing that the machine does is it recursively processes X. Okay? So this is one transition. and then the rest is just recursion. Okay? So I can define the behavior of a finite state machine as saying, if there's no input left, stay put. Otherwise, use the transition function to decide what to do when you read the first character, and then give it to the recursion fairy. Okay. Now, of course, this will, in practice, this expands, right? So this recursion is, in some sense, that for loop that I put in the original algorithm. It's like read the first character and recurse. That's the same as for all characters in order. Okay. So for the machine that we saw earlier, here's an explicit computation of the, what you get if you start in state 0 and you read 001011101110, which, if I have done this correctly, is binary for 374. And you just sort of grind through the recursion until eventually you reach state 4, which is 374 mod 5. Okay? Now, so what happens is the state machine starts in state 0. It applies this function delta star to the input string by scanning one character at a time. And then if the machine ends in an accepting state, the machine accepts. The light bulb goes off, the machine says ding, you get Skittles. If you end in a state that is not in the set A, it's not an accepting state, then the machine rejects. The light bulb does not go off, you get a sad trombone, and you don't get Skittles. Okay? And so in this particular machine, I read that string of characters. I'm going to end up in state 4, and because 4 is not equal to 0, the machine stops and says, wah, 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 and you get nothing. Okay? Now, there is again, when you're dealing with specific examples like this is not the right notation to be using. I'm basically showing it to you here to make sure that you understand what the notation means. But if I were doing this as a specific example, the right notation to use, I think, is the one that I've written down here at the bottom. I started in state 0. I read symbol 0, and that put me in state 0. I read symbol 0, and that put me in state 0. I read symbol 1, that put me in state 1. Read 0, go to 2. Read 1, go to 0. Read 1, go to 1. Read 1, go to 3. Read 0, go to 1. Read 1, go to 3. 1, go to 2. 0, go to 4. All right, so I get this sequence of states separated by arrows where over each arrow I write the symbol that caused that transition. And this is calling back to this graph, right, where I think of the states as nodes, and I think of the transitions are specified by these directed edges. So what I'm doing when I write down the sequence of states and transitions is I'm specifying a walk in that graph. Okay? So I can think of it like this. So I start in state 0. I read 0 and I go here. And then I read 0 again and I go here. Then I read 1. Then I read 0. Then I read 1. Then I read 1. Then I read 1. Then I read 0. Then I read 1. Then I read 1. Then I read 0, and I end here. And any string of zeros and ones is going to specify a unique walk in this graph, starting from the start state, and ending at sigma star of S comma W, where the transition function sends me if I start at S and I read string W. Okay? So I'm deliberately trying to show you multiple ways of thinking about this at the same time. And the reason I'm doing that is not because I don't want you, it's not because I want to get you confused, although that may be the effect it's having. The reason that I wanted to show you multiple ways of thinking about this is it's always useful to have multiple ways of thinking about things. I would like you to be able to comfortably switch back and forth between, oh, here's this delta notation that I can use if I want to write things down formally, to, well, here's this arrow notation I can use to be a bit more intuitive and suggestive, to, well, I'm really thinking about a walk in a particular graph whose edges are labeled in a particular way, instead of having a big lookup table or an explicit function. Because in different contexts, different kinds of different formulations are going to be more or less useful. And in the end, they're all equivalent. In the end, they're all perfectly reasonable, perfectly formal, perfectly valid ways of thinking about it. The reason why the notation, as ugly as it is for this common example, shows up is that if we want to prove general things about arbitrary finite state machines, it's really hard to do it with the circles and arrows because we don't know what the circles and arrows are. So are there any questions about what this function does? I'm sorry? Oh, I'm sorry. Yes, I can try. Okay. Process the first symbol, recurse. All right, so let me show you another example. And I want you to attempt to tell me what this machine does. Sorry, let me start again. Okay, so I'm going to have an alphabet, which is 0 and 1. I'm going to have two states, which, because I don't really want the two states to have the same name as the input alphabet, I'm just going to call them S and T. S is the start symbol. The only accepting state here is going to be T. And my transition function is this. If I read a 0, I stay in the same state. If I read a 1, I go to the other state. Okay? Now, if I want to draw a picture of this machine, so the machine has two states, one called S, one called T. The S is the start state, so I'm going to draw an arrow coming from outer space and pointing to that S. The only accepting state is T, so I'm going to draw a double circle here. And now I have to draw 4 arrows. So there's an arrow leaving S that's labeled with a 0. That points back to S. There's an arrow leaving S labeled with a 1. That points to T. There's an arrow labeled T with a 1 that points back to T. And, 0. And there's a label, outgoing arrow from T labeled with a 1 that goes back to S. Right. This machine accepts strings if and only if they satisfy some condition. What condition? This machine accepts a string if and only if the number of ones in this string is odd. Right, so this is the language that this machine accepts. Strings with an odd number of ones. And this leads to probably the point of all this is that we're not only using these finite state machines to describe algorithms, we're also using these finite state machines to describe languages, right? For any finite state machine, there is a set of strings that that finite state machine accepts. The language of the machine, which I sometimes write L of M, where M is this collection of stuff, okay? Or M is the machine specified by that drawing, right? There's an adjective that one might use to describe what kinds of languages could possibly be accepted by a finite state automaton. And the etymologically correct term to use here is automatic. A language is automatic if and only if there's an automaton that accepts it. But the word that we'll actually use is regular. No, it's not. I'm not overloading the term. A language is accepted by a finite state machine if and only if that language can be described by a regular expression. This is no way obvious. It is absolutely not obvious that this is true, but it is. Okay? And eventually we'll actually get to the point where we can prove it. So a language is regular if and only if it can be described by a regular expression or it is accepted by a finite state automaton. Now, different sources disagree on which one of these bullets is the definition and which one is the theorem. Right? I'm going to hark back to Kleene, who defined regular languages as the things that are described by regular expressions, and then proved that those are also the things that are accepted by finite state automata. Lenny will tell you something different. Yes?
So just to clarify, every finite state automata.
No, so remember, the same regular language can be described by infinitely many different regular expressions, and similarly, the same regular language is accepted by infinitely many different finite state machines. There's no correspondence between a particular finite state machine and a particular regular expression. Okay? There are ways of deriving finite state machines from regular expressions, but there's more than one way to do that. We'll see one of them later. And there are ways of deriving regular expressions from finite state machines, but again, there's more than one way to do that. Okay? So the correspondence is just if there is a regular expression that describes the language, if and only if there is a finite state machine that describes the language. But those two are not necessarily related in any real sense. Now, I want to go through this an exercise, and I want to go through it once, in part just to show you what's involved. Not because this is the sort of thing that we will expect you to be able to do, or to want to do, or to have time to do, but to point out that in principle this is something you could do if you were willing to invest the time. And to give you at least a high-level picture of how you would argue that a given finite state machine is actually correct. Okay? I've made this claim, which is correct, that this finite state machine accepts all strings and only the strings that have an odd number of ones. That's a fairly non-trivial statement, actually, right? Because it involves both, a fair amount of actual information about what the machine is and a not really completely trivial description of what the language is either. So, you know this is coming. How do you prove this? Induction. Great. On what? Okay. So I'm going to, again, another sort of template. Suppose I have two sets, A and B. How do I prove that these two sets are equal? No. This is actually one of the few cases where that's not the right answer. Okay, so this is, I'm asking a question at the same level of, suppose I want to prove a statement that starts for all. How do I do that? And the answer is, bow to your sensei. Let X be an arbitrary element of the set, and then whatever you're trying to prove at the bottom. And then you decide, maybe I want to do induction, maybe I want to do something else. Okay? So this is sort of a higher level thing. Even before you start thinking about induction, you say, oh, I'm trying to prove two sets are equal. How do you do it? Yeah?
You show A is a subset of B and B is a subset of B.
Right. So there are two states. You prove first that A is a subset of B, and then second, you prove that B is a subset of A. Great. Awesome. Absolutely correct. Now, let me push that one more step. How do you prove that A is a subset of B? What does it mean for A to be a subset of B? One at a time. Yeah. Right. So for every element, let's call it little a in capital A, we have little a is also in B. Great. All right, last push. How do you prove, what is the first line of the proof for this statement? Bow to your sensei. Let A be an arbitrary element of A, and then I have to do some work, and I conclude, so A belongs to B. Okay? Now, 9 times out of 10, what goes on in that box? Induction. But now the question is, what are you doing induction over? You're doing induction essentially over the kind of thing that you invoked when you bowed to your sensei. You're doing induction over the elements of A. And you're doing that by exploiting somehow some definition for A. Right? So in here, you're probably doing induction on A, whatever that means. Right? And similarly, if I want to prove that set B is a subset of set A, the way that I would start that proof is I would say, let B be an arbitrary element of set B, and then I would conclude, so in fact B is an element of A. And inside this box, I'm probably going to be doing induction on this element B. Okay? And this is how you prove the two sets are equal. Whatever those two sets are. Now, it may or may not actually really honestly need to use induction in those two boxes, but more often than not, yeah, that's what you're going to do, especially if these are sets of strings. Okay? Now, for the particular problem I have here, A is the set of all strings with an odd number of ones. Okay, so when I'm doing induction on a set of strings with a certain property, what does that mean? What are my cases going to be? A is now going to be some string with an odd number of ones, and I want to prove that the machine accepts it. What are my, I'm going to do induction on A. What that means is I'm going to look at the cases of the definition of string with an odd number of ones. And that definition is it's either empty or it isn't. Okay? On the other hand, in the second line, I'm going to be looking at all strings that the machine accepts. And the recursive definition of a machine that a string that the machine accepts is right here. So again, it's going to be based on either the string is empty or it isn't. But you should really think of this as doing induction on the number of transitions, as opposed to doing induction on the number of symbols. Okay. So this is the high-level picture I want you to take away. Let me actually show you the proof. Okay? Now, I'm not going to write it because it's here in the notes. I'm just going to sort of walk through the proof fairly quickly. Okay? Now, inevitably, stop! Inevitably, when you want to prove something like this, you actually need to prove something stronger. It's not usually enough just to prove this is the set of strings that's accepted by the machine. What you really need to prove is no matter what state I start in and no matter what string I read, here's what I'm going to get. Right? This is a complete description of the behavior of the machine, not only in terms of what it accepts and what it doesn't, but no matter where I start, no matter what string I read, this tells me what state I should end up in. Now, unfortunately, that means there are 4 things to prove. If I start in state S and my string has an even number of zeros, then I end up at state S. If I start in state S and I have an odd number of zeros, I end up in state T, and so on. And unfortunately, these things are sort of mutual. The proofs are going to require you to prove all 4 of these things simultaneously. So if I start in state S and I read a symbol 1, I go over to state T, and now I have to argue inductively about what happens when I start in state T. And moreover, if I had a string with an odd number of 1s, I've just read a 1. Now what's left has an even number of 1s. Okay. So I need to prove this stronger statement. All right, so I'm going to start, this is a statement about what happens given an arbitrary state and an arbitrary string. And you notice that it's exhaustive. I've considered every possible state and every possible string. Yes?
Sir, why do you have to prove what happens when you start in state?
Okay, so I'm always going to start in state S, right? And let's suppose, because this is one of the things that can happen, is the first thing I do is I read the symbol 1. And now I'm going to recurse, which means I need my induction hypothesis to tell me something about what happens when if I were to start the machine in state T, right? This is something that will show up over and over and over when we're talking about recursion. When you want to prove things, something by induction, you have to make or describe an algorithm that does something recursively. You really have to make sure that the thing that you're analyzing takes into account what happens when you do the recursive call, which may not exactly resemble the original problem that you're trying to solve. Okay. So, for any string W, that's what I need to prove. Since this is a theorem about for any string W, I bow to my sensei. Let W be an arbitrary string. And then I'm going to do induction. So, assume for any string X that is shorter than W, we have, and then I rewrite out the theorem using X instead of W everywhere. And now there are 5 cases to consider. Now, I didn't come up with the number 5 first. First, I wrote out the cases, then I went back and typed 5 on that line in the text file. Okay? But one of the cases I need to consider is what happens when the input string is empty. Well, in this case, I stay in the state that I start in. So delta star of S comma epsilon is S. Delta star of T comma epsilon is T. This is just by definition of delta star. And sure enough, the empty string has an even number of 1s, and so the theorem is correct when W is the empty string. Okay? All right, next. Now, the four remaining cases are all, suppose the string starts with a 1 or it starts with a 0, and suppose the string has an even number of 1s or an odd number of 1s. Okay? And I'm only going to show one of those four because, like it says, since the rest of the cases are similar, I'll leave out the line by line. Okay? But for this one string, I say, okay, suppose W starts with a 1 and X is everything else. And W has an even number of 1s. Then X has an odd number of 1s, and so the induction hypothesis tells us something. It says, if I start in state S, I'll end up in state T if I read X. And so now I just grind through the definitions. If I start in state S and I read string W, that sends me to this complicated expression. That's just the definition of delta star. And then delta of S comma 1 is T because that's the definition of the transition function delta. There it is. And then delta star T comma X is S because X has an odd number of 1s and X is shorter, so that I get by the induction hypothesis. Similarly, if I start in T and I read W, then I end up at T. First by the definition of delta star, then by the specification of delta, and then by the induction hypothesis. So in the end, I actually end up doing 9 3-line proofs. Right? 1 for the empty string, or maybe it's 10 3-line proofs. 2 for the empty string, depending on whether I started S or T, and then 1 branch for the choice of the first character in W, 1 branch for the choice of whether I'm even or odd, and 1 branch depending on whether I'm starting in S or starting in T. And so I get this unholy mess. Now, this is not complicated. The core of the proof is these 3 lines. Just depending on which case I'm in, I might have an S or a T here, and I might have an S or a T here. That box in blue is all that's really going on. It's just long because it's going on 8 times. Right? What I want you to be able to do is argue about one of those cases. Right? If I start in this state and I read an even number of 1s, where am I going to end up and why? Right? The fact that all the other arguments are identical, you just go, yeah, symmetry. Okay? But I want you to follow the logic for that one argument. Right? It just expand the definition of delta star, plug in the definition of delta, then apply the induction hypothesis. That's it. Okay? Now, as you might imagine, these proofs tend to get a bit more complicated when you start looking at bigger machines, like, say, this one. Right? So if I want to do a similar proof for that 5-state machine, I'd have to basically argue if I start in state 0, 1, 2, 3, 4, that's 5 different options, and I read in a number that is, whose residue mod 5 is 0, 1, 2, 3, 4, then I'm going to end up in some state, and then in my proofs I have an option of whether I read a 0 or whether I read a 1, so I need 50 different inductive arguments. Or I could do math and reduce it all down to 1. By carefully designing the transition function like this. And just arguing, instead of separating out all the different cases separately, explicitly, remembering that I know how modular arithmetic works and using that. In general, the finite state machines that we're going to have you design are likely to have somewhere between 2 and a dozen states. We're not going to ask you to prove these things are correct, not because it's hard, but because it's boring. Okay? Nevertheless, as you're designing it, as you're thinking about it, you should always have in the back of your mind, this is what it means for the machine to accept something. Did I get this right? So if I assume the right thing inductively, yeah, okay, I can do spot checks. Right? This is what the graders are going to be doing. They're going to be spot checking. Right? And if you don't have the sort of formal definitions in mind when you're designing these things, it's actually fairly easy to be led astray into doing things that are just not right. Okay. All right. I want to close by, very quickly looking at the clock and realizing that whenever I have the tendency to say I've got only one more thing, and there's less than 10 minutes in the class, the appropriate thing to do is to shoot myself in the head. We're done. See you on Tuesday. I'm happy to answer questions. Thanks.
Question about the homework. So I am just trying to understand the